Welcome back to the Deep Dive. This is the show where we take a big stack of research, some pretty dense technical notes, and sort of the on-the-ground industry realities.
Yeah.
And we boil it all down into something sharp and actionable so you know exactly where to put your time and your money.
And today we're tackling a question that, I think comes up for pretty much anyone who moves past the basic off-the-shelf AI. And that is all the effort of fine-tuning an automatic speech recognition model, an ASR model, is it really worth it for, a single bespoke user?
Exactly. I mean, our listener here is looking for something more than that, 85% solution you get from a huge general model like Whisper. They have really specific needs. They're doing constant code switching, mixing English with other terms. They're using deep technical jargon, and they have an accent that sometimes, trips up the general models.
So our mission today really is to give you a clear cost-benefit analysis, but one that's tailored specifically for that individual user. We're going to unpack sources that look at, why you'd even want to fine-tune in the first place, the strategy behind using smaller models, and I think this is critical. We're going to contrast what a solo user does with these multi-million-dollar mission-critical enterprise solutions.
So we're really figuring out what you actually gain in usability, what the real cost is in terms of effort, and I guess why the whole ecosystem is still so frustratingly complex. Why isn't there just a simple, fine-tune for dummies platform out there?
That's the core of it. I mean, look, the general accuracy of ASR today it's pretty good. It's good enough for, casual stuff. But that leap from pretty good to truly reliable and ready for my workflow, that almost always requires specialization. And that's exactly what fine-tuning is for.
Okay, so let's dig into that. Let's unpack this core problem that I think faces anyone who wants to build their own custom AI. You look at the raw numbers. I mean, a model like Whisper is trained on, 680,000 hours of audio?
A staggering amount.
Yeah, it feels like you're trying to nudge this massive cargo ship just by, flicking a pebble at it. So if I fine-tune this giant model on my own little custom data set and I only get a 2 or 3% gain in accuracy, why on earth would I bother? What's the real value there?
And that's the right question to ask, because that impulse to just dismiss a 3% gain is totally understandable. But for ASR, you really have to reframe what modest even means. For this kind of work, a small absolute improvement in, say, word error rate or WER, it doesn't translate to a small benefit. It translates into these disproportionately massive gains in usability.
Okay, so you're not trying to teach it English from scratch.
No, not at all. The model already knows English. You're just teaching it the very specific, very high-stakes exceptions to the rules that are absolutely critical for your unique way of working.
So let's get specific. Let's start with those things that general models are just terrible at. Our listener mentions code switching, mixing English and Hebrew terms in the same sentence. Why do the big models fail so spectacularly at that?
It's because of how they're trained. A model like Whisper, it's a transformer, and it's generally trained on these big piles of data that are, sorted by language. So when it hears a seamless, rapid shift, like an English sentence with the Hebrew word mekolet for convenience store, the two main parts of the model, the acoustic model and the language model, they start to fight each other.
A fight. That's a great way to put it. So what does that fight actually look like in the final text?
Well, the model has what we call very high language model priors for English. It expects English words. It predicts English words. So when it hears the sounds for mekolet, which are just statistically weird for an English sentence, it basically tries to force those sounds into the closest English phones it can find.
So instead of I went to the mekolet, you might get something like I went to the make-a-lot.
Exactly, or just some other complete nonsense that forces you to stop what you're doing and manually correct it every single time. And the thing is, without fine-tuning, the error rate on those specific mixed language words is basically 100%. It will get it wrong every time.
So fine-tuning isn't teaching it a whole new dictionary then?
No, it's teaching it the pattern.
Okay.
It's normalizing that mixture. It's basically sending a signal to the language model part that says, hey, megalit, or gRPC. That's a valid and expected word in this specific English context.
Okay, that right there makes it seem worthwhile. You're fixing an entire category of errors that are otherwise just unavoidable. But then there's the other big one for professionals, the technical jargon.
Yeah, and this is critical. Standard models really struggle with technical vocabulary for a couple of reasons. The first is just rarity. Terms like PyTorch or, specific industry acronyms, they're just not common in that huge 680,000 hour general data set.
And the second reason is more subtle, right? The homophones.
Yes, the homophone problem is it's so insidious because the word it gives you is a correct word. It's just completely wrong in that context. Think about CEDAW versus cooler or cash versus cash.
Right.
In fast dictation, the acoustic cues can be ambiguous, so the general model just defaults to whatever's statistically more common. Cash. Cooler. That leads to some really confusing or even embarrassing mistakes when you're talking about a high-stakes technical term.
Yeah, that moves from just being annoying to being completely unusable really fast.
Precisely. What fine-tuning does is it adjusts those language model priors for your specific world. It teaches the model that when it hears NVIDIA and GPU, the next word is overwhelmingly likely to be CEDAW and capitalized correctly, not cooler. You're basically stacking the deck in favor of your specialized terms.
So it's less about teaching it new words and more like reweighting the probabilities based on the context you provide.
That's a perfect way to describe it. You're just recalibrating its statistical expectations for someone who talks about code all day versus someone who talks about, I don't know, cooking.
Okay, let's go back to the numbers and try to quantify this.
Yeah.
You mentioned a 2 to 5% absolute reduction in war is a huge deal. Can you break down what you mean by this usability cliff? How does that small number turn into such a big subjective win?
The usability cliff is all about cognitive load. It's that threshold where the amount of effort you have to spend correcting the machine drops so much that it actually changes your behavior. So let's just compare an 8% ER with a 5% AR.
Okay, so 8%, that's what? One wrong word in every 12, roughly.
Mm-hmm.
And 5% is 1 in every 20.
Correct. And at 8% ER, you're pretty much guaranteed to have at least one error, probably more, in every single short sentence. This forces you to constantly interrupt yourself. You're dictating, you're checking the screen, you're backspacing, you're redictating. You totally lose your train of thought.
And the mental energy you waste just fighting the system is massive.
Exactly. You're spending your brain power on fixing the machine's mistakes instead of on what you're actually trying to create. But when you cross that cliff, when you get down to 5% or 4% ER, the system goes from being unreliable to being reliable. You go from having multiple errors per sentence to maybe 1 or 2 errors in an entire paragraph.
So you start to trust it.
You trust it implicitly. You can just dictate your full thought and then, go back and clean up a few minor things at the end. The need for that constant mid-sentence correction just plummets. That tiny statistical difference from 8% to 5% can translate into something like an 80% reduction in how often you hit the backspace key.
That makes perfect sense. The cost of correcting that 12th word is so much higher because it breaks your flow.
It's the difference between a high-friction tool and a low-friction one. And it's not just about the vocabulary. It's also about personal voice adaptation. This is where all those little cumulative gains really add up.
Tell me more about that, especially for what you called minority accents, like Israeli English, which probably isn't a huge part of the Whisper training set.
Well, it's super effective because you're tuning the model to your specific accent patterns, your speaking pace, your rhythm, and, critically, your co-articulation quirks. Co-articulation is just how the sounds in your speech blend together, like how in did you, the D and the Y often merge into a J sound.
The natural slurring of speech.
Right. And a general model is tuned for the most common co-articulation patterns, say, from North American English. If your accent has slightly different blending rules, or if your pacing is different, the model is constantly making these tiny little misinterpretations that add up.
So fine-tuning is fixing those small acoustic errors. At the same time, it's fixing the big vocabulary errors.
Exactly.
Yeah.
And that's why the cumulative effect of that 2 to 5% gain feels like such a huge leap in usability. The model it sounds more confident when it hears you. It feels more accurate. You stop fighting the tool and you just start using it.
Okay, so to get this level of personalization, you need to put in the work. You have to collect and transcribe your own audio. So how much data are we really talking about for an individual user?
We usually break it down into 3 tiers. For just some basic adaptation, getting your accent right and maybe a few dozen key terms, the absolute bare minimum is probably around 30 to 60 minutes of good, clean audio. You'll see a little improvement.
But to cross that usability cliff, to really feel the difference.
For a truly noticeable improvement, the practical minimum is more like 2 to 5 hours of high-quality, domain-specific audio. That's really the volume you need to start shifting the model's weights in a meaningful way.
And what if you have, say, deep technical content with hundreds of unique industry terms?
Then you probably want to aim for 10 to 20 hours. That gives the model enough repetition and variety to really learn your specific world and make a tuning robust so it works well in different situations.
Now, this brings up an interesting point. I think a lot of people have this intuition that if you want to teach the model a new word, like PyTorch, you should try to isolate it. Minimize the surrounding words to increase the signal-to-noise ratio.
That intuition, it makes perfect sense on the surface, but for these modern transformer models like Whisper, it's actually wrong. You should absolutely not be training on isolated words. The context is not noise. The context is crucial signal.
But why? If the model already knows 90% of the sentence, why include all that extra stuff?
It's because of how the learning process, gradient descent, actually works. When you're training, the model compares its prediction to the correct text for the entire clip of audio. And the gradient, which is basically the correction signal, it automatically focuses the learning effort on the parts where the error was highest.
Oh, so it self-prioritizes. It already knows the and I am, so the correction there is tiny.
Exactly. It's basically saying my error on I am going to the is almost 0, so I'm not going to waste my time there. But my error on this new word gRPC is massive, so I'm putting 90% of my learning effort into fixing the weights that cause that specific mistake.
So the context almost acts like a spotlight, highlighting the exact thing that needs to be fixed.
Precisely. And on top of that, the context provides all that vital information about co-articulation, how the English words blend into the technical term. It also helps the language model learn the statistical probability of that word appearing in that specific situation. So no, context is your friend. It stabilizes and enriches the learning.
That's a huge takeaway. Maximize context, don't strip it out. What about the length of the audio chunks? We know Whisper was trained on 30-second segments.
Right, and that 30-second limit is a hard architectural constraint. You can't get around it. But for data gathering, the user's preference for chunks that are around 20 to 30 seconds long is actually perfect. It's really strategic.
Why is that better than, say, a bunch of 10-second clips?
Because 20 to 30 seconds is long enough to capture natural narrative flow. It captures prosody, the rhythm and intonation of your speech, and the full context of a thought. It just makes the data collection way more efficient than recording hundreds of short, isolated phrases, and you're still staying safely under that 30-second hard limit.
All right, so let's shift from the why of fine-tuning to the how. Specifically, how you deploy this thing. For an individual user, they're often constrained by their local hardware. Maybe they have a consumer GPU, or maybe an AMD card, which historically has been a pain for AI stuff. Should they still be trying to fine-tune the biggest model possible?
This is where we get to a really key strategic insight for the solo user, and that is the huge practical advantage of fine-tuning the smaller models. If your priorities are local control and keeping costs down, aiming for the biggest model like Whisper Large is usually the wrong move.
Tell us about this idea, the crossover effect. What's the technical reason that fine-tuning Whisper Small or Tiny is such a good strategy?
The observation is really about where the models start from. The big models, like medium and large, they start off extremely accurate. Their weights are already highly optimized and pretty rigid because they generalize so well. The smaller models, like tiny or small, they start with much higher error rates. They just don't have the capacity to generalize as well.
And how is that an advantage for fine-tuning?
Because they have so much more room to improve. Their initial weights are, you could say, softer or less fixed, which makes them incredibly receptive to a small amount of high-quality specific data. When you feed that small model, say 5 or 10 hours of your voice and your jargon, the absolute drop in the error rate is just way, way bigger than what you'd get from applying that same effort to the already great large model.
So a fine-tuned small model is a totally different beast from the off-the-shelf small model.
Completely different, and that's the crossover. A well-tuned Whisper small model can reach an accuracy level that gets very close to, or sometimes even matches, a stock unmodified Whisper medium model, which is 3 times larger, but only on your specific voice and your specific vocabulary.
So if a stock medium model gives me, say, 8% ER on my technical audio, what could I expect from a fine-tuned small?
Well, In that same scenario, the stock small might start out at, I don't know, 12% ER. But after you fine-tune it on your 10 hours of data, its wear could drop dramatically down to maybe 6% or 7%. It has literally crossed over and is now outperforming the larger stock model for your specific tasks.
And the practical benefits of that for local deployment are obvious.
They're massive. The goal here isn't just raw accuracy. It's fast, local, private, and offline inference. A fine-tuned small model runs almost instantly on consumer hardware. Trying to run a fine-tuned large model would mean either expensive cloud APIs or a huge amount of local VRAM, and you'd be sacrificing privacy and control for maybe a tiny 1-2% accuracy bump. The crossover effect makes a smaller model the clear strategic choice.
Okay, so once you have that fine-tuned model, it needs a home. It needs to be accessible, maybe 24/7. What are the realistic options for a solo user who needs fast, reliable access without getting hit with enterprise-level bills?
Yeah, you have to weigh the options carefully because the cost profiles change a lot based on how much you use it.
Let's start with the easiest ones, the zero-setup serverless options.
Right, so platforms like Replicate, Modal, or Hugging Face endpoints are amazing for testing and for occasional use. You only pay for the processing time. If you're only transcribing a few hours of audio a month, your bill might be, $5 to $20. The problem is the pricing curve is really steep. If you're a heavy user doing continuous dictation, those costs can explode into hundreds, maybe even $1,000 a month. It's not a solution for an always-on system.
Agreed. So then you pivot to owning the hardware, or at least renting it. What about a cloud VPS, but sticking to CPU only to keep costs down?
A CPU-only cloud server from a place like Hetzner or another dedicated provider is much more stable in terms of cost. You're looking at maybe $35 to $50 a month. The predictable cost is great. The trade-off is speed. For a model like Whisper Large, your processing speed is going to be about real time or maybe even a bit slower. That's fine if you're just batching up long notes and don't need instant results.
Which brings us to what you called the cost champion for heavy use, local deployment. And our listener has an AMD GPU, which is key here.
Yeah, this is the hands-down winner for long-term cost and performance. If you run your fine-tuned small model locally on your own desktop using an optimized engine, the only ongoing cost is basically electricity, maybe $15 to $30 a month. And for that, you get instant inference speed, total privacy, and the lowest possible long-term cost.
Okay, but I have to push back a bit there. Even $30 a month in electricity, plus the initial cost of training, that's not nothing compared to a free service from Google or Apple. And more importantly, what about the maintenance headache? I mean, self-hosting means you're now a sysadmin. Doesn't the predictability of a $50 a month cloud server make it worth it for someone who just wants the thing to work?
That's an excellent point, and the maintenance headache is absolutely the hidden cost. If you're not comfortable with Linux, with networking, with security, then yes, the cloud BPS is probably worth the extra $20 a month for the peace of mind. But for a user who is technically savvy, the local option offers things the cloud can't. Absolute privacy. Your audio never leaves your house, and that sub-second inference speed that makes dictation feel truly instantaneous. It's a trade-off. Technical effort versus long-term cost and control.
That's a good way to frame it. But if you do go local and you want to access it from, say, your phone, you had a big warning about port forwarding.
A crucial point, never ever just open a port on your router directly to the internet. You have to use a secure tunneling service, something like Cloudflare Tunnel or Tailscale. They're usually free for personal use, and they basically eliminate almost all of the risk by creating a secure, encrypted connection to your machine.
Got it. So let's talk about the process itself. For getting the absolute best accuracy on long-form notes, is it better to dictate live, streaming to the model, or to record the whole thing first and then process it in a batch?
For raw accuracy, batch transcription is demonstrably consistently better than live streaming, and it all comes down to architectural freedom.
How so? If it's the same fine-tuned model, why does the processing method matter?
Because batch processing removes the biggest constraint, real-time latency. When you process the whole audio file at once, the model can use what we call full bidirectional context. It doesn't just look backward, what you just said. It can also look forward at what's coming up later in the audio.
And how does looking forward help it fix mistakes?
So imagine you say a sentence that starts with an ambiguous word, like, I need to check the cache. The sound could be cache or cache. A live system has to make a decision right now and will probably default to cache. But in batch mode, if the next phrase in the audio is dot validation protocols, the model sees that future context and realizes you must have meant the technical term cache. It can go back and correct its own prediction.
That capability alone seems like it would provide a huge accuracy boost for technical stuff.
It does, and on top of that, batch processing allows for way better preprocessing. You can run sophisticated noise removal on the entire file first, and critically, you can do optimal segmentation. Instead of just chopping the audio every 30 seconds, the system can analyze the whole file and make cuts at natural pauses. This drastically reduces those annoying boundary errors where a word gets clipped in half.
So if I record a complex 15-minute note on my phone, uploading that file for batch processing is pretty much always going to be more accurate than using a live dictation app.
Generally, yes. The improvement, especially for dense, jargon-heavy content, can easily be 5 to 20% better in terms of word error rate. It's just because the model gets to use all of its strength: full context, cleaner audio, and better post-processing.
We've made a really strong case for the solo user fine-tuning for their own workflow. But that's, the low-stakes end of the spectrum. I want to contrast that with the highest-stakes environments, the mission-critical enterprise. What does this look like when an organization needs, near-zero error tolerance?
Yeah, this contrast is so important for understanding why personal fine-tuning is achievable. But perfect ASR is still a multi-million-dollar problem. For the bespoke user, it's about usability and cost control. For the enterprise, it's about human safety and ironclad regulatory compliance.
Okay, let's quickly recap the individual side one more time. The drivers are privacy, local control, so your ongoing cost is almost nothing, and solving those unique problems like code switching that the general models just can't handle.
And the outcome is immediate. Your workflow improves, the cognitive load of dictation drops, and the tech goes from being a novelty to an essential tool. You can achieve it with consumer hardware and a few weeks of effort.
Now, the enterprise side. We're talking about air traffic control or high-stakes medical transcription. What's their acceptable level of error?
It's effectively zero. In a medical setting, an 8% ER is lethal. In air traffic control, one misheard number for an altitude can cause a catastrophe. Their goal isn't just saving time, it's preventing failure and meeting legal standards of precision.
So what kind of investment are we talking about to get to that level of perfection in both time and money?
These are major, long-term institutional projects. You're typically looking at a life cycle of 2 to 4 years to get a system fully deployed and certified. And the costs, they're astronomical. Anywhere from $2 million to over $10 million for the custom development, integration, and ongoing maintenance.
$10 million. That's a staggering number. What are they spending that on, beyond just training a bigger model?
They're spending it on things the solo user never touches: proprietary data, multi-layered systems, and certification. First, custom data collection is mandatory, it's expensive, and it's slow.
Why can't they just use the same public data sets we use and fine-tune them?
Because those public sets don't match the acoustic environment. For air traffic control, they need certified audio from actual control towers, with all the specific radio static, the background noise, multiple people talking at once, all of it. Collecting and transcribing tens of thousands of hours that gold standard audio can take over a year and cost millions.
So accuracy comes from perfectly matching the training data to the real-world environment.
Exactly. And second, they build these incredibly complex, multi-layered systems. It's not just one model. They might have multiple ASR engines running in parallel and use fancy fusion techniques to pick the most confident output from all of them.
And what else is in that stack?
They'll have highly specialized language models trained only on medical or aviation terms. And they often have real-time confidence scoring, a separate AI that's just predicting the accuracy of the transcription. If that confidence score drops below, say, 97%, the system automatically flags it for a human to review immediately. The whole thing is designed to catch that last 1% of errors.
So why can't a big commercial API like OpenAI or DeepGram serve these clients? If they're offering 95% accuracy, why spend $10 million?
Two big reasons: the residual accuracy gap and regulatory failure. First, that gap is just too big. A general model might hit 5% ER on clean speech, but on noisy, technical, mission-critical audio, that can easily jump to 15 or 20%. These systems need to be certified below 3% and ideally below 1%.
And the regulatory side is a non-starter.
A total non-starter. You can't send HIPAA-protected patient data or federally regulated aviation data to a public third-party cloud API. It's illegal and operationally impossible. Compliance demands total data sovereignty. These systems have to run on-premise or in a certified private cloud.
So the companies that do this are super specialized.
Precisely. You're talking about niche specialists like Nuance for medical or defense contractors like Saab Census for air traffic control. They sell certified platforms and long-term support contracts. For them, ASR is critical infrastructure, not just a simple API call.
That contrast really drives home the complexity. So let's bring it back to the consumer space. Given how clear the demand is for personalized models and how relatively easy it is to fine-tune these smaller models, why isn't there a single user-friendly platform for this? Why is it still such a DIY, roll-your-own kind of project?
That's the core frustration, isn't it? And the simple answer is that a modern, usable speech-to-text app isn't just one model. It's more like a synchronized symphony of 4 to 6 different AI components. And when you customize just one part, the ASR core, you're suddenly on the hook for managing the whole complex orchestra.
Okay, let's call this multi-model orchestration. What are these hidden pieces that every good STT app needs?
Right, so when you hit record and get a nice, clean transcript, you've actually run a pipeline. It usually starts with voice activity detection, or VAD, which just filters out the silence. Then you might have a wake word detector. Then comes the actual ASR model, like Whisper. And after that, you need punctuation restoration and maybe diarization to figure out who's speaking.
So the VAD and the wake word are kind of always listening in the background.
Exactly. They're tiny, lightweight models running in real time. The ASR model is the big, heavy lifter that runs in bursts. And then the punctuation and diarization are post-processing steps. The challenge for a platform is integrating all of those and managing the resources, especially GPU memory, on a local machine.
It sounds like coordinating a pit crew. Everyone has to do their job in the right sequence, but only when they're needed.
That's a great analogy. And if you fine-tune Whisper, you're only upgrading one part of that crew. You still have to figure out how to plug in a good diarization model or a robust VAD. If your VE fails and feeds a bunch of silence to your perfectly tuned ASR model, your accuracy still tanks. The system fails at the seams.
Let's talk about punctuation versus paragraphs. This is a huge usability gap. You said Whisper handles punctuation pretty well on its own, but it completely fails on paragraph breaks. Why does it get one and not the other?
It's all about the training data. Whisper is good at punctuation because it was trained on millions of hours of punctuated subtitles and captions. So the model learned that, at the end of a sentence, there's usually a period or a question mark. It sees those as predictable features of language.
But paragraphs are just invisible to it.
Totally invisible. Because paragraph breaks require a much higher level of understanding. It's about topic shifts, about discourse structure. And the short captions Whisper was trained on, they don't have paragraphs. Plus, it's subjective. There's no sound you make that means start a new paragraph now.
So to solve that, a platform would need yet another major AI component.
Absolutely. The current best practice for adding paragraph breaks isn't another ASR model. It's an LLM, a large language model like Claude or GPT that you run in a post-processing step. You feed the clean transcript to the LLM and prompt it to insert paragraph breaks based on topic flow. And that need for an external, heavy LLM is a massive architectural barrier for a simple, fast, local platform.
Right. And beyond that complex architecture, there's just the fragmentation of the ecosystem. Whisper is dominant, but it's not just Whisper. It's like a dozen different optimized versions of Whisper.
Exactly. Whisper dominates because it's open and it's good out of the box. But if you're building a real app, the original PyTorch model is just too slow. You need a specialized engine for speed.
Let's focus on the ones that matter for a bespoke user, especially our listener with an AMD graphics card.
Okay, so they really need to be looking at implementations that are optimized for speed and compatibility. The first big one is Faster Whisper. It's built on an engine called C-Translate 2, and it gives you about a 4 times speed up. And crucially, C-Translate 2 has support for AMD GPUs through ROCm.
We mentioned ROCm before, but let's quickly define that. What is it?
So ROCm is AMD's open source software platform. It's basically their answer to NVIDIA's pseudo. For years, if you wanted to do serious AI, you needed an NVIDIA card. ROCm is what finally allows users with AMD cards to get that critical GPU acceleration for AI workloads. So Faster Whisper using C-Translate 2 is the go-to for high-speed production on non-NVIDIA hardware.
That's essential info. What about for really constrained environments like a phone?
Then you'd look at something like Distill Whisper. It's a distilled version that's about half the size and 2 to 3 times faster, with only a tiny drop in accuracy. And for ultimate portability, for running on a CPU with no GPU at all, there's Whisper.cpp. That's a pure C++ implementation that's highly optimized to run pretty much anywhere.
And this brings us to what you call the model format maze. You fine-tune a model, you get this nice .safe file. Why can't you just use that one file everywhere?
Because every one of those specialized runtimes requires its own specialized optimized format to get that speed. The safe tensors file is great for training, but to get that 4x speed up on your desktop with faster Whisper, you have to convert it into the ctranslate2 format.
And what if you want to run it on your laptop CPU?
Then you need to convert it to the GGUF format. GGUF is the modern standard for CPU-only and edge deployment. It's a quantized format, which means the model's weights are stored with less precision. That makes the file size way smaller and lets it run efficiently on a normal CPU without needing a dedicated GPU.
So depending on whether I want max speed on my AMD GPU or efficiency on my laptop CPU, I need completely different conversion tools and workflows.
Exactly. And that requirement to manage, convert, and maintain all these different specialized formats, ctranslate2, GGUF, maybe ONX for cross-platform stuff, it adds this enormous layer of complexity. A simple consumer platform just can't abstract all that away and still offer peak performance on all hardware. And that's a big reason why the market is still so fragmented.
Okay, so to wrap this all up, the big question we started with, is fine-tuning worth the effort for an individual user? It sounds like the answer is a definitive yes.
It's a definitive yes if your workflow involves specialized language, jargon, or a non-standard accent. The return on investment isn't in that small, raw accuracy gain.
Right, it's in the massive improvement in workflow and usability. That 2 to 5% drop in error rate is what gets you over the usability cliff. It eliminates the frustration and lets you actually integrate the tool into your daily life, especially for things like code switching.
And the best strategy for doing it is to use that crossover effect. Fine-tune a smaller model, Whisper small or tiny on 5 to 10 hours of your own high-quality, context-rich data. You end up with the accuracy of a bigger stock model, but with the speed, privacy, and low cost of running it locally.
And we also saw that huge gap between a free open-source model and the kind of near perfection required by a $10 million enterprise system. That gap isn't going to be closed by one single breakthrough. It's going to be closed by relentless incremental engineering.
Which leads us to our final thought. The frontier of ASR research isn't just about recognizing words anymore. It's now about understanding structure. Paragraphs, who's speaking, the semantic context, maybe even the emotional context. And given all that complexity, the next generation of ASR won't just transcribe better, it will fundamentally understand and structure knowledge better.
That idea of structural understanding, turning a raw wall of text into a clean, segmented, shareable document, that's what turns a simple transcript into actual, useful knowledge.
ASR is evolving from just being a dictation tool into a knowledge organization tool. The models of the future won't just spit out text. They'll spit out perfectly formatted markdown with headers, bullet points, and speaker labels, all driven by this deeper contextual awareness.
And that journey from raw text to structured knowledge feels like the next big hurdle for personal productivity AI. So if you're ready to start your own fine-tuning journey, you now know which models to aim for, why context is everything, and why local deployment is your most powerful option.
Until next time, keep digging deeper.